Hello everyone, thanks for tuning in on this video on homogeneous second order differential equations. Really this is just to identify what our kind of three major cases are when we have this kind of scenario where it is in the below form and A, B and C are all constants in this case. Why is it called homogeneous? Well, remember, a non-homogeneous differential equation is when we can get our what's called independent variable, a function of that independent variable on the right-hand side without anything else. Since this thing equals to 0, it means we have no other function on our right-hand side, and therefore this is called a homogeneous problem. So when you have something equal to 0 in this form, this is a homogeneous problem. And bear in mind this is linear as well. So these are kind of our easiest cases and what we'll be doing in FP2. There'll be another video on non-homogeneous cases when this thing on the right hand side is a function of x. But for now what we're going to try and do is identify our three cases that we could face in this situation. Okay? Right. The first thing to bear in mind is how to solve this thing, how to view this thing. Well, I think the easiest way to look at this is that this thing has been made if you consider a function of y, a function y that is, to do with x. If you differentiate this thing once, twice, times it by a constant both times and add them all together, does it equal 0? That's what we're looking at. Is there a function that exists that behaves in this way? What function can we think of that differentiates to itself, basically, and if you times it by a few constants, it's going to cancel itself out? Well, there's one that I can think of, and that's why, again, it's such a special function. It's this letting y equal e to the x. But not just, e to the x, there's got to be something there, hasn't there, to do with e to the x, because e to the x does differentiate to itself. That's why it's special. But we also need this constant m on there, where m is a constant, because as we know, when e to the mx differentiates, our m is going to pop down, and that will help us build a multiplier such that, like I say, when you differentiate this once, twice, times it by something, add them together, they're going to cancel each other out and end up with a result of 0. So what we've got here is what's called our complementary function, our starting function. And complementary functions are always concerned with when the right-hand side is 0 of our homogeneous second order differential equation. And that's the same for non-homogeneous problems as well. We would treat this, well, we'll talk about that later, but we're going to treat it as it equals 0, and then we'll deal with a function thereafter, okay? But let's think about this then. So let's say this was our starting function. If I differentiate this once, so I get dy over dx is me to the mx, and if I differentiate it one more time, I'm going to get m squared e to the mx. If I were to plug these things back in here then, remember this is meant to equal 0. So I would get a m squared e to the mx, that's this thing plugged back in here. And then I would get plus b m e to the mx, that's this thing plugged back in here, plus our c m e to the mx, that's this thing back into here. And this should equal 0 if this is true. What we need to do is identify the conditions that this then will equal 0. So you can notice here that we could take out a factor of mx. So what we get is am squared plus bm plus c. Oh, I've copied that down wrong, haven't I? For our, there shouldn't be an m. There we go. Cool. Plus c equals 0. We know that e to the mx, remember the graph of any exponential function looks like this. If m is positive or if it's negative, it's going to look like this. But the point is it's never going to equal 0. It's always above 0. So this does not equal 0, and therefore we can't really consider that. What is going to make our whole differential equation 0 is this am squared plus bm plus c. And this is where we build up our conditions of our three cases. Because if we put this in the quadratic formula, what we get is, we get am squared plus bm plus c equals 0, which implies that m equals minus b plus or minus, and here we go, b squared minus 4ac over 2a, our normal quadratic formula here. This equation is actually very special. This is called our auxiliary equation, which we will abbreviate to AE, because mathematicians are lazy. Alright, let's call our auxiliary equation. What we need to do is investigate what happens when m changes in this way. It's going to sound a little bit complicated, but actually it's fine once you get going. It's actually quite algorithmic, but it's interesting what's happening here. The thing to note, though, is that this yc equals e to the mx is true. But notice if I put an a on the front, another constant on the front, this is also true as well, isn't it? This a would just pop out here when you differentiate it. It's just going to stay on the left-hand side. We'd have big A's in there as well then. Big A in there as well. And we would get a big A on the outside here as well. So already, what I'm saying is that when we start with our complementary function, these problems, it can be an infinite number of complementary functions because A, as a constant, can be anything. So from now on, we're going to start our problems with yc equals a e to the mx. Right, so first case, what we need to do is consider when b squared minus 4ac, our discriminant for m, is positive. If it's positive, nothing changes, does it? We will have two values of m though, won't we? We'll get m1 is minus b plus b squared minus 4ac over 2a, and we'll get m2 is minus b minus b squared minus 4ac over 2a. So case 1, what we're saying is that our complementary function, i.e. in this case, because it's homogeneous and it equals 0, this is also acts as our general solution, is in the form of a e to the mx, but remember m can be one of two things, so minus b plus b squared minus 4ac over 2ax plus b e to the minus b squared minus 4ac over 2ax. Why can't I just plus them like that? Well, let's think about it. If I just isolated this section, remember if I differentiate that once, twice, add it all together, this will equal 0. If I do the same thing to this on the right hand side, differentiate it once, twice, this will equal to 0. So if I plus them together, it can be, this thing will still equal 0, because as we know, if you differentiate one thing plus the differential of another, that is the same as differentiating them both at the same time. So it makes sense that what we have is, we've got in our first case, yc is ae to the m1x plus be to the m2x, where a and b are constants, and m1 and m2 are when the discriminant of b squared minus 4ac is greater than 0. Right, so this time we're going to investigate case 2, where b squared minus 4ac equals 0. So what we're left with is m is minus b over 2a. So you would expect that our complementary and therefore general solution function here is going to be ae to the minus b over 2ax, which is understandable, but what maybe is a little bit more confusing is that also bx times our minus b over 2ax produces the same result only when, so if and only if, b squared minus 4ac equals 0. Now, it would be really great if you could validate this for yourself. I mean, we know that plussing two functions together and differentiating them isn't a problem, as long as both functions differentiate once, twice, add to themselves, times by this thing is going to equal 0. So it would be great if you could validate that this is the case. So what I want you to do is let yc equal bx e to the minus b over 2ax, and differentiate it once, twice, and have a go, and make sure it does equal 0, and then I'll do it. So 5, 4, pause the video, give it a try, 3, 2, go on, try it, 1. Okay, well done for trying. So, let's see if we match up. If I differentiate this, we should get b, I'll do this quickly because you've already done it, or maybe you're just stuck in a certain place. So we're there, and this is the product rule, so b e to the minus b over 2ax, that's all good. We're going to differentiate again, and this time, don't forget that minus there, this is going to be product rule again, so minus b, little b, 2ax, and then, so hard to write in this crappy pen. Okay, 2a over x, and then we've got the product rule, like I say, so we're going to differentiate this thing this time, so we're going to get plus big B, little b squared. I can't take myself seriously saying big B, little b, but okay. Here we go, and then we're going to differentiate this thing, which is going to go to minus big B, little b, 2a e to the minus b over 2a. X. Now, if I plug all this stuff into here, well, I'll just tidy this bit up first, this and this, add those together, you're going to get minus big B, little b, over a, e to the minus b over 2a, x, plus big B, little b squared, x over 4a squared, e to the minus b over 2a, x. So, if I shrink all this down, and start whacking all this back into our original formula, which is here, what I end up with is minus big B, little b, I just cannot say that, 2ax times by a plus big B, little b all squared, 4a, x e to the minus b over 2ax, and then we're timesing this thing by b this time. So minus big B, little b all squared over 2ax e to the minus b over 2ax plus big B, little b e to the minus b over 2ax. And then we've got this plus, sorry, that should say a y here. Okay, that should say a cy equals 0. Apologies about that. So, cy plus cy, and c, as we know, b squared minus 4ac is 0, so therefore c is b squared over 4a. So we have b squared over 4a, and then our function yc, which is bx e to the minus b over 2ax. Does this all cancel out? Yes, it does. We have this thing cancels this plus this equals b squared over 2ax, and then it cancels here, so it does equal 0, and we're happy. So that should be validated now. So to conclude, what we're saying there is if b squared minus 4ac equals 0, then our general solution or complementary function here is ae to the mx plus bx e to the mx. And that's our case 2. So when we have repeated roots for m, whereas before we had real roots for m. Well, just 2 distinct real roots for m, sorry. Okay, so this time we have b squared minus 4ac is negative, which means in here we're going to have a square root of a negative number, which we can't do, or which we would need to start converting to I, wouldn't we? So, since b squared minus 4ac is negative, I could write m as being minus b plus or minus, and this is over 2a, square root of minus 1. Ouch, it hurts. I shouldn't be writing it, I know. Don't tell anyone. I hope your nose isn't bleeding right now. But just for that illustration, this thing, as we know, is I. So we've got minus b over 2a plus or minus I square root 4ac minus b squared over 2a in this case, which means our complementary function is now ae to the minus b over 2a x times by, well, actually I'll slow that down. So we've got ae to the m, remember. So we've got ae to the minus b over 2a plus square root, with I in the front, 4ac minus b squared over 2a, x plus b e to the minus b over 2a minus I square root 4ac minus b squared over 2a x. And this thing is actually okay, it's like a valid solution, but it would never be written this way. We would simplify this down. And how we can do that? Well, we can notice we have an e to the minus b over 2a x straight away as a factor, don't we? So e to the minus b over 2a x all times by, and what we're left with is ae to the I root 4ac minus b squared over 2a x plus b e to the minus I square root 4ac minus b squared over 2a x. Now, what can we do with this? This can be written in a different way as well. If you remember from FP1, putting stuff in mod arg form, you should know that e to the I theta is the same as cos theta plus I sine theta. This is found via the Maclaurin series. So if you've seen the Maclaurin series before, then you'll know about it. If you haven't, you'll learn about it in FP2, you can watch some videos on it, blah, 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 blah. But that is a really interesting and cool fact that e to the I theta can be written in that way. And that means we can replace our theta with square root 4ac minus b squared all over 2a times by x. So we can now write this as e to the minus b over 2a x, and now we've got a cos, and then our theta is going to be root 4ac minus b squared over 2a x plus I sine square root 4ac minus b squared over 2a x plus b lots of this thing now, but with minus. So cos minus 4ac minus b squared over 2a x. Just shrink that down. Plus I sine of our minus 4ac minus b squared over 2a x. Now, what we need to recognize here is that this thing, this cos of minus 4ac minus b squared all rooted over 2a, we need to know that cos itself is an even function. So i.e. cos, if you have f of minus x, this is the same as f of x. Look at the graphs, they're symmetrical about the y-axis, that's what it means by an even function. Cos of minus 45 is the same as cos 45, which means that this minus in here is actually the same as the positive version, the positive angle inside. Similarly, or oppositely, I should say, the odd function is sine. So f of minus x is the same as minus f of x. Think about it, sine of minus 90 is the same as minus sine of 90. So this thing is actually now minus I sine of the positive angle square root 4ac minus b squared over 2ax. So we can write this in a different way again. So minus b over 2ax, and this time I'm going to multiply out at the same time these brackets. So a cos square root 4ac minus b squared over 2ax plus ai sine square root 4ac minus b squared over 2ax plus b cos. And remember, this minus here is now a positive because it's exactly the same thing. So 4ac minus b squared over 2ax. And then we're going to have our next section, but remember this minus comes outside here. So we're going to have minus bi sine square root 4ac minus b squared over 2ax. And we can start recognizing common factors here. This cos and this cos is the same, and this sine is the same. So we get e to the minus b over 2ax. We get cos square root 4ac minus b squared over 2ax. And this is all times by its factor a and its factor plus b. Plus, and now we're doing the same with sine, so sine square root 4ac minus b squared over 2ax, and this time the ai comes out here and the minus bi comes out here. Well, what is this a plus b? Well, that's just a constant, isn't it? So we'll call that a. And ai minus bi, well, that's just a constant as well. It doesn't matter if it's complex, it's still a complex, it's still a number, it's still a constant, so we'll call that b. So what we end up with is e to the minus b over 2ax, a cos square root 4ac minus b squared over 2ax plus b sine root 4ac minus b squared over 2ax, which, notice, can be finally simplified down in a similar fashion to what we did before, but involving m. So this is e to the real part of m times by x, remember, in brackets a cos the imaginary part of m times x plus b sine the imaginary part of m x here as our angles. And we're done. That's it. That's all three cases. There'll be another video on examples on actually how to use this, but this tells you exactly where all these results come from.